We are going to be deriving a formula that we are going to use to find an electric field by a finite line. So by a finite line we mean, just underline it here, finite line we mean a line that has a known length. So this derivation could be of a line of an infinite line. It could be a line that goes from negative infinity up to positive infinity, but for our case it's a finite line of a length of, and just write the length of our line is going to be 2a, because from here to here is a, then from here to a is a, then if I add them up then I have 2a. Okay, sharp. So then how do we do that? Okay, here we have a line that okay, let me say here I have a point here, and then this finite line is having an electric field toward this point, which is pushing it this way. But because we're looking at something like a line, it has some small part of it, like the one red that I just highlighted here, just some part that is actually exerting a force. Let me just fix my thing. Okay, now I'm good. That is actually exerting a force to here. Okay, so we know by our formulas that if we given a problem like this where there is a point, a charge and a test charge, we could have just said an electric field at that point should equals to k q the charge and r squared the distance between them. But in this case we're looking at the small charge, not just the whole plate, a small charge that is exerting here, right? So if you look at the small charge, we're actually looking at let me just call it dq, right? And this dq, I just said this one is dq, this one is dq. It is x distance, and this hypotenuse, let me just call it r, and you know I'm saying hypotenuse because of this right triangle, and then it should be giving a hint that most likely we'll be using Pythagorean theorem in a way. So okay, so this point charge is exerting or is causing electric field at this one. Okay, so this is a charge, so this electric field that we will be discussing, it will be also a d electric field, a small or just a 1 electric field if there's anything like that. Okay, and then it's going to equals to k is a constant, and for q we're going to use our dq all over. For r, this is our r, right, the one I just called hypotenuse. It's called big R here, but I can just do it out. It's going to be x squared. It's going to be x squared, or let me say r is equal to x squared plus a squared all under a root. This is just because of Pythagoras theorem. And okay, good. Then I will have to substitute this r inside here with this my traditional formula. Because there is a square here and there is a square root here, they negate each other, or you just cancel that. Then I'll have to have here x squared plus a squared. Okay, also what is important is that when I'm talking about the small charge, the dq here, as I put it here as dq, it is not exactly, or should I say, we need to get a proportion of the dq toward the whole line. So we have something called linear to take note of this one. We have something called linear charge density. In basic terms, this is like how much charge per because we're talking about a line per length. How much charge per length. So that is represented by a symbol lambda, of which I just said it's how much per length. Okay. So with that being said, we can now say that on dq, the small part, we are going to get, we have to take and you also know that dq here, I have supposed to mention here, dq is dx in terms of length. Okay, so I'll have to say it is dx in terms of length, so it's going to be dx, the length, and multiply by the ratio or linear charge density, of which is like this. So in terms of instead of dq, we are going to use this. Okay, and then we are going to plug it just here instead of dq. So we're going to have lambda dx. Okay, we are getting somewhere now. So this is where we are in 6 minutes. Let's look what we can do after this one. Okay, also you should notice that since we are talking about dE, we are literally talking about an electric field caused by this small part. But this small part, there are a lot of them causing this electric field at this point. So we are supposed to sum them up. So you know this fancy summing, it's going to be integral, right? So we're supposed to add all the dE's, all the electric field, all the small electric field caused by any point within the line. Okay, and then we are adding all the dE's from negative a to a, from the start of the rod, or should I say the line, till the end of the line. Also, I think it is very useful to notice that the electric field caused by this dx is going to go this way. Okay, that means it has y and x component. Okay, this is our dE that we are talking about, dE. Also, let me say there was another point. Let me say I'm trying to put my attention to another point at the same position as this one, but bottom, which is also causing an electric field to here. That was supposed to be more accurate. Okay, something like that. And then that will also be causing dE. Okay, if you notice now, you have vectors like this, the one going like this, and you have another vector going like this, and we know that if I add them up, they're going to give me a vector like this, because they are made of both x and y, and this one is also and y. And then we can notice also that the y cancels because they are of different direction, but also only x's vectors add up. So with that information, we can conclude that here we are only looking at the dEx, because anyway the dEy are going to vanish anyway. They're going to cancel each other since this is symmetrical. But if this thing, or should I say, if this point or this line wasn't in the center, was up or down, it would have been a different case. It would have been more complicated and quite complex to integrate, but it's quite doable. Okay, then to find the vector, should I say the electric field vector along x, we'll have to use cos. This angle is the same let me say this angle is the same as this one because of vertical opposites, also this one and this one. Okay, so we can say, if I call this thing, let me call it alpha, cos alpha should equal to adjacent, of which from here to here we said it was a was there for that. It's now like an angle. Okay, it's adjacent a all over hypotenuse, and our hypotenuse was what? I had it written here, but I remember I removed it. It was x squared plus y a squared, I mean, all under a root. Okay, so this is our cosine theta, right? And also remember we talked about something. We said I'll have to redraw those vectors again. There was something like this. This was DE and this one was DEX. Now I'm interested on the DEX. This is alpha is here. Okay, so to get this one we'll have to say let me say cos of alpha will have to equal to adjacent, of which is DEX all over hypotenuse, of which is DE. Okay, that's good. And then to get DEX, that means DEX will have to equal to DE cos alpha. That's supposed to be cos alpha. Why I'm writing x? Okay, just alpha. You will know that it was supposed to be alpha. Okay, good. Then I can now remove all of this just to clear my space. And now we have DE here, but we have DEX here, but we only have an expression for DE. So we're just going to apply this and put it just back here. And hope you know how I work this out, and you can just scroll back to the video and try to figure it out. Okay, so it's going to be negative a, and then for dx, we know dx is going to be de. We have an expression for de here, right? Okay, de is going to be k lambda dx all over x squared plus a squared. And it is also worth noticing that we also have cos alpha here, of which we already have an expression for it. This was our cos alpha here. And then cos alpha is going to be a all over x squared plus a squared all under a root. I've used this. Let me just clear it out. Okay, also if you don't know where some part is from, you can just go back to the video. This was from there. Okay, I also don't need it now. Okay, now I'm in this expression. Because this thing is symmetrical, if it was a function, if we were talking about math, I would have said it's an even function. For an even function, integrating from here to here is the same as starting here to here. Is the same as, let me just use okay, integrating from here to here is the same as integrating only the upper part, same as focusing only the upper part and then multiplying it by 2, because they are symmetrical, they are the same. So I can remove the negative, and then now okay, if I remove the negative here, I'll only integrate from 0 to a and multiply by 2. So I'll have a 2 here waiting for me, and then go here, and then now I'll integrate from 0 to a of k alpha dx all over x plus a squared multiplied by a all over x squared plus a squared, that is under root from Pythagoras. Then I still go down. Okay, what do I do next? Okay, let me think. Okay, because I'm integrating, I can just factor out all the constants, like what is not changing. Remember, I have a diagram. Let me just go back. Let's look at k. K is a constant. It's obviously out 2k. I already have 2k. Let's look at dx. Okay, dx is in terms of x, obviously changing. Let's look at a. Let's go back here. A was this distance from here to here, right? So as I'm moving from here to here, a is not changing, if you can notice. So if a is not changing, a is also a constant. Let me just put it here. A, k, and then a also goes out. And let's see what I have left. And now I have to integrate from 0 to a of what? Of dx, and here these are of same bases. If they're of same bases, I can just add the exponent, right? Plus a squared, and if I add, this is power 1, this is power root is 1 over 2, remember? So I'm having 1 plus 1 over 2, I think it's 3 all over 2. Also, let me say this problem was changed to be, maybe they said this was finite. Let me say if that they said that thing was infinite, the one that is producing this electrical field. So I was saying if this was infinite, the only thing would have changed would have these boundaries. They would have been infinite, negative, up to positive infinity. So depending on the scenario, the only thing that can change from this derivation could be your boundaries. Okay, others could be given yeah, it's just that yeah. And then what else? Oh, about this integral, it's a very well-known integral. You can check on my math playlist, so you can see how we can do this, but I'll just give you the answer from here because physics is done. So if I integrate this, also there's something that I miss here. Lambda is a constant that's supposed to go out. It's here, it's also here. Okay, if I integrate this, and then I'll have a all over a squared, I think, and x, no, open, is going to be x squared plus a squared, and here is going to be 1 over 2, and then the boundaries is 0 up to a. Okay, you can do the math here. Okay, also here it's supposed to be x. I made a mistake. Okay, now and then now we have to do the final minus initial. So our initial, it's final minus initial. Our initial is 0, so we don't have to worry about it, because if you put 0, everything disappears. A, k, lambda, and then open brackets, and then if I put a here, it's going to be a, and then it's going to be a squared. I should have noticed this a is also a constant now from here, but it's okay. X squared. Oh, instead of x, then I put a again. A squared plus a there was confusion of variables here. Now I understand why I'm having a lot of a's. I call this thing a while I already have an a here for a distance. So the a that is in the formula here, let me call it big A. Just that I made up the formula from here. I mean the problem from here. That's why I'm having a lot of errors. Okay, so that's good. Yeah, I think so far I'm good. And then the other part is going to be with 0, so it's going to be to disappear. And again, also this a was supposed to be a big A, is it? Okay, this one is is a constant, right? It's not changing because this A is this A. Okay, a big A according to me. Okay, it's also supposed to be big, and that's also supposed to be big. And now I can cancel one of these A's, I mean this one and this one, and then here now I will have please point out if you see any errors, but I think I'm doing good now. This A will be now on the K lambda. There was an A here, also a big A for K. This is a small a multiplied by, here on the bottom it's going to be A for length. Let me just call it length. Yeah, if I call it length, that means the whole thing is length over 2. Okay, sorry for changing variables. I wasn't prepared making the problem. I just made it from my head. Okay, A squared. So A is for the distance from the point to the line, and the length L is from here to here. That means here I have minus L. So I'm just changing my variables in the end. Okay, so I think this is the result that you should expect. But I advise you to, from here, I think my job for physics ended just here. Onwards is just your integrations going down. This is your calculus up to this. This was supposed to be 1/2 up to this answer. Also, again, notice that here this is an electric field along the x, because we said this is the only electric field that is going to remain, since the y and the y are going to cancel each other. So I hope you find this video informative, and if there's something that you don't understand, you can just hit me in the comment section, or maybe email me. There's my email on the page. I'll also do another one for the ring. I think I'll also do another one for the plate. Yeah, because there could be a point here and there will be this ring exiting. You can see some kind of a conic electric field. So thank you. Please don't forget to subscribe, share the video with your classmates and everyone who might need it. Thank you.